Okay, so yeah, it's my pleasure to introduce Michael Cecil. He's a graduate student in Max Planck Institute in Heidelberg. So I met him not too long ago in an invited talk in Toronto. And I thought, who's this bright student? And then we talked, and later he said, hey, I've read all of your papers. So I was very happy. And then I realized he is from Austria, from Burgenland. So he doesn't live very far from here. So I said, you should come and give a seminar at our institute. And Michael is here. He did his master's from Vienna and his PhD. It's his third year, and he's about to graduate, and he has published 3 papers in 3 years, so very productive. And today he'll be talking about inner protoplanetary disk, MSD simulations, radiation MSD simulation, and some interesting stuff. So Michael, go ahead.
Okay. Thank you very much, Kundan, and hello, everybody. My name is Michael. I'm just about to finish my PhD at the Max Planck Institute for Astronomy in Heidelberg, in Germany. But as Kundan said, I'm not from Germany. I'm from here, from Austria, just about 2 hours from here is where I grew up. And it's an honor for me to be here today and to talk to you a little bit about the work that we've been doing over the last about 3 years on the topic of structure, evolution, and instability of the inner regions of protoplanetary disks. Now, I admit, while this title might explain perfectly well what we are investigating, it might not be the catchiest title for a talk like this, or for a thesis for that matter. So let's go for something a little bit more crafty, shall we? Something like, if that works, doesn't work.
The mouse has to be on the window.
But it's not working.
Now it works.
Ah, okay.
Yeah. So something like raving with the stars. So this is a very fitting title for this kind of project, not only because over the last 3 years I was able and fortunate enough to work with some of the absolute superstars of our field of research, but also because what we are dealing with here are young stellar objects that show large variability in their luminosity in the form of bursts of light, like a strobe light at a rave. And so sticking with the theme of a rave, we are going to start off with some pre-drinks in a sort of pre-burst phase, and then we're going to dance in the disco strobe light that the burst is providing us with, before we then have to fight through the inevitable hangover that is going to come afterwards. Until it's then finally time to start the party all over again. But first, let's have a look at what the objects are that we're actually investigating here. So this is a protoplanetary disk, a large, mysterious object made out of gas and dust that is revolving around its central newborn star. And eventually, all the planets that we know and love from our solar system, and most of the planets that we are observing today, are formed out of those disks. And if we want to know how this happens, we have to study their structure and their evolution. So let's take a cross-section of one of those disks and look at it from the side to see the vertical structure. So this is the disk made out of gas and dust, and it is connected to the central star via the stellar magnetic field. And those disks are primarily accretion disks, meaning that angular momentum in these disks has to be transported away in order for the material to drift towards the star and be accreted onto the stellar surface. And there are 2 main mechanisms with which this angular momentum transport can happen. And one of them is the one that we are focusing on today, and this is turbulence. So turbulent motions inside the disk are transporting angular momentum outwards and allowing the disk material to be accreted inwards. And generally, we can divide the disk into 3 main regions of different levels of turbulence. Starting from the very inner regions, where we expect very high levels of turbulence and very efficient angular momentum transport. Going to intermediate distances, we expect a region with low levels of turbulence. This is what we call the dead zone. So where the angular momentum transport is less efficient, this is the brownish region in here. And in the very outer regions of the disk, we may expect high levels of turbulence again. But the most interesting regions for us to look at are actually those transition regions in turbulence. Because whenever you have a transition in turbulence, you have a mismatch in mass or angular momentum transport, which means that this can lead to accumulation of material locally at those transition regions. So for example, you can imagine that as the material is drifting inwards quite efficiently due to the possibly high levels of turbulence, it's crashing into the slow-moving dead zone, and this creates some sort of traffic jam effect here at the interface. And those accumulations of material are, of course, pristine locations for forming the seeds of planets and growing dust into planetesimals. And a very similar process is happening here at the inner edge of the dead zone as well. And those inner regions of the disk, they have been very elusive in the past, both from an observational and theoretical standpoint, because of their closeness to the central star and the very short time and spatial scales on which all different and difficult physics are happening in the inner disk. But this is the region that our work is focused on. And the motivation to look at those inner regions is also pretty much straightforward. So here we see a temperature map in the radial vertical plane, and distance-wise, here is where we would find Mercury today. Here is Venus, here is Earth, and here is Mars. And here are about 85% of all the exoplanets that we have detected to date. They are located about within 2 astronomical units from the central star. Of course, there's a lot of observational selection bias to that, but it seems to be the case that a lot of planets are located very close to the star. And if we want to find out how they ended up there, we need to understand what the protoplanetary disk was doing at the beginning. So we are looking at this inner disk structure and its evolution in terms of radiation-hydrodynamics. And in this framework, the 3 main processes that are determining the inner disk structure are those 3 here. So the irradiation by the central star, a contribution to the heating by turbulence. So turbulence is not only responsible for removing angular momentum, but also contributes to the heating. And as a cooling mechanism, we have radiation again. So the disk material radiating its energy away. And in the interplay of those 3 processes, we get 2 important transitions within the inner disk region. The first one is the dust sublimation front, here shown in green. So in here, the temperatures are so high due to the stellar irradiation that the dust sublimates and goes into the gas phase, leaving us only with the gaseous component. And out here, gas and dust can exist simultaneously. And the second transition is the one that I've already mentioned before. It's closely connected to the dust sublimation front, and that is the turbulence transition, or the inner edge of the dead zone, here shown in black. And this manifests itself due to the activation of the so-called magnetorotational instability, or MRI. The only thing we need to know about the MRI for our purposes right now is that it produces very high levels of turbulence and is a very efficient angular momentum transport mechanism. So in here, the MRI can be active in this high temperature, high ionization degree region, which means that the angular momentum transport is very efficient in here. And out here, the MRI cannot be active, and this creates a so-called dead zone and very low levels of turbulence. And the transition between those 2 is typically modeled with a simple temperature threshold. So above this TMRI, the MRI can be active, and below it, it will be inactive. So this is the general structure of what we currently think the inner disk has. But at the beginning of our project, we just simply asked the question, is this structure stable over long periods of time? And as you may have guessed, we found that it is indeed probably not stable. So how can it become unstable? So I've already mentioned that those turbulence transitions are often associated with accumulations of material. And this is exactly what is happening here as well. So due to the difference in angular momentum transport efficiency between the inner MRI active region and the dead zone, the density in here will slowly start to build up. And as the density increases, the temperature will increase as well, because this region becomes more optically thick. It cannot radiate its energy away as efficiently, and the temperature eventually can reach the activation temperature of the MRI. And then suddenly, this region, this high density region, will become highly turbulent. That leads to a runaway heating process, and the whole thing blows up. But now let's get the party started. So our investigation of the inner disk evolution is separated into 3 main episodes. And we start off with the simplest model that we could come up with, although nothing about that is really simple. But this is the same structure that we just saw before. But now we're going to evolve this in time. And this is what we are seeing. So the MRI gets activated and the MRI active region expands far into the inner disk, making it highly turbulent. Now, interestingly enough, this is a process that is going back and forth a few times in so-called flares or reflares. And it's consecutively dumping all the material from the inner disk onto the star by making it highly turbulent. And eventually, the instability sort of fizzles away and the quiescent, more or less stable structure of the inner disk is reestablished. Probably more importantly than the temperature map is the density evolution. So down here, we see a density map in the background, and in the foreground in red, this is the column density. And we're going to ignore this purple dashed line for now. And if we evolve this in time again, what we see is that this instability mechanism completely rearranges the density structure of the inner disk. It produces these spikes in density that are pushed ahead of the expanding MRI active region and are then placed in the inner disk. And because each of those reflares is weaker than the previous one, there are multiple such spikes placed throughout the inner disk. And those spikes are super interesting for us to look at because they are associated with pressure maxima in the disk. And pressure maxima are generally capable of trapping solid material and dust within them and allowing the dust to grow into larger bodies such as planetesimals or planets. And as a last diagnostic of this instability mechanism, we're going to look at the accretion rate onto the central star. So as this high density region is made highly turbulent, it gives off its angular momentum and is dumped onto the star very efficiently. And this will leave an imprint on the accretion rate. And indeed, this is what we are seeing. So the accretion rate jumps up by about 2 orders of magnitude as this instability is developing. And each of those reflares will then add an additional bump to the accretion rate curve. And the accretion rate is basically our direct connection to observations, because such accretion rate curves are observable, and we do indeed observe a lot of young stellar objects out there that show large variations in their accretion rates. So let's stick with the accretion rates for a moment. What we just saw was just one small part within a much larger simulation. So here we evolved the disk for multiple thousands of years, and there are 2 such full instability cycles that we have just seen occurring here. One at the beginning and one after about 2,500 years. And they are separated by a long quiescent phase or hangover phase in between. So what this shows is that this instability mechanism produces periodic accretion outbursts that are observable onto the central star. And the timescales, so the timescale of the quiescent phase in between and the timescale of the burst itself, it's highly dependent on pretty much anything we put into our codes. So for example, the mass of the star and the disk, or the turbulence levels that we prescribe, the luminosity of the star, and so on and so forth. But probably more importantly than the accretion rate is the effect of those bursts on the structure of the inner disk and on the conditions for planet formation and migration. Here we see a space-time plot with the radius on the x-axis and time on the y-axis, and the surface density or column density color-coded. And those white lines and dots show the locations of pressure maxima within the disk. And as I mentioned before, those pressure maxima are super important to look at for us because they are pristine locations for forming planetesimals and planets. And we see, for example, there is this pressure bump here coming into the picture before the instability phase. And this is one that has already been known in the literature for some time as being a very strong and stable pressure maximum that can even trap migrating planets within it, and is therefore a good candidate for explaining why a lot of planets are ending up in this region. But as we can see, as the instability is rushing through, the pressure bump is destroyed and is only reinstated after the instability has died down. But at the same time, there are multiple other pressure maxima created by this instability mechanism, which are all of them by themselves capable of trapping solid material within them and growing planetesimals or disturbing the migration of planets. After the instability phase, we go over to the quiescent phase. And during quiescence, the inner disk is refilled with material that is flowing in from the outer disk because it has been drained with material by the burst. So we are seeing here the time evolution of the column density during the quiescent phase. So we start off after the instability with this bluest line, where we still see some of the bumps. And over the course of the quiescent phase, the density will slowly increase due to the accumulation of material at the dead zone inner edge. And what the disk aims at is establishing a sort of hydrostatic state, which is shown here as this yellow dashed line. But it can never reach this state, because as soon as this pinkest line here is established, a new instability cycle starts, and we are resetting the density to this bluest line, and the whole cycle starts again. So this instability mechanism periodically and completely rearranges the inner disk structure in terms of density and pressure. And this, of course, can have significant consequences on the formation and migration of planets throughout the inner disk. So this is what we have found in the first episode of our project, which was published about 1.5 years ago, that the inner disk is intrinsically unstable, and it produces periodic accretion outbursts that can significantly rearrange the density structure of the inner disk on a periodic basis. But there were two major concerns that we had with our simple models at the beginning. And one of them was when we consider that this outburst mechanism is a highly thermal process at its core. And also the structure of the inner disk is given by the thermodynamics in the inner disk region. And the thermodynamics is determined by those three processes. And the one quantity that has the most influence on those processes is the opacity of the inner disk material. So the opacity is the efficiency with which energy can get transported through the disk, or with which energy can get absorbed and radiated away again. So the opacity is one of the central deciding quantities determining the inner disk evolution. At least so we thought. So in our simple model, we used a relatively simple description for the opacities. So you can assign opacities to the dust and the gas component. And we did so, but by just choosing a constant value for the opacity for gas and dust separately. And also for the efficiency of the irradiation absorption from the central star, we used one constant opacity, which is, of course, not super realistic because the opacities depend on many, many different things. But that led us to the structure that we've seen before, to the evolution of these instability mechanisms. So it was a natural next step for us to take to improve upon this description. And we did so by choosing new opacity models. Yeah, there we go. And for the dust, for example, we used the Diana standards, which is originating from one of Peter's works. And for the gas, we used calculations that were done at MPIA a few years ago. And we were even able to treat the irradiation in a frequency-dependent manner. So we separated the spectrum of the star into different spectral bands, and each band had its own opacity. And that led us to an inner disk structure that looked like this. So if we look at the temperature scaling, here it's linear and here it's logarithmic. And that shows us that the influence of the opacity is pretty strong on the structure of the inner disk. And as it turns out, the most significant impact comes from the gas opacities. So that the dust opacities themselves do not have such a strong influence on the overall structure of the inner disk. But the gas opacities are the ones that matter the most. And typically, gas opacities are sometimes neglected in the investigation of protoplanetary disks, because as long as some dust is present, it will always dominate the opacities, and the gas opacities basically don't matter. But here, we are in a regime where the dust is sublimating, and only the gas phase is left. That's why the gas opacities should not be neglected here. However, we still have this instability mechanism to deal with. And we can do this by comparing the accretion rate curves of our simple model from before in blue and the new improved opacity model in orange. And the only real difference between those two is that the quiescent phase in between is a bit longer. But this is not surprising at all, because everything we put into the code has an influence on the quiescent phase timescale. And if we look at the bursts themselves, what we see is that they don't look all that different at all. They last the same amount of time. The peak accretion rate is the same. They still show this reflaring behavior. So it seems like, although the gas opacities or the opacity description has a huge influence on the structure of the inner disk, it does not have an effect, not a significant effect, on the outburst mechanism. And this was actually quite surprising for us, because we saw how many weird things, especially those gas opacities, are doing to the inner disk. But they don't seem to have any effect on the outburst mechanism, which means that everything that we found from our simplest model from before is still applicable with very different descriptions of the opacity. And to find out why the gas opacities don't matter here at all, we have to look at the outburst state itself. This is what we are seeing here. The MRI active region has reached its largest extent, and the dust in this viscously heated region here has started to sublimate. But what we may notice is that in here, the temperatures are almost constant. They have hit some sort of plateau, it seems. And this is due to a so-called thermostat effect that is created by the dust sublimation. This is a phenomenon that has been recognized in the literature already, amongst other, of course, by Peter himself. And this thermostat effect, it prevents the temperatures from reaching even higher values. What this also means is that in here, as long as the thermostat effect is active, there will always be some dust present in this region. And as long as some dust is present, the gas opacities will never dominate. And this is the reason why the burst mechanism is not affected at all by the gas opacities. Okay, so having dealt with the opacity problem, we have seen that while they have an effect on the structure, they don't have a significant effect on the instability mechanism. But the second major concern that we had was with how we describe the activation of the MRI, because this is, after all, what this instability mechanism relies on, the activation of the MRI in this high-density region. And up until now, we have only described this with a very simple temperature threshold, saying that above this temperature, the MRI is active, and below, it's not active. But of course, the MRI is much more complicated than just being dependent on the temperature. It mainly depends on the ionization degree within the inner disk and the magnetization, so the presence of magnetic fields. And those of you who have heard my talk on Tuesday may suspect what is coming next, because in order to find out where the MRI and when the MRI is active and when it's not, we have to face one of the most dreadful questions that we always get asked in each of our talks when we present our work somewhere. And this is, what about magnetic fields? And the magnetohydrodynamic, or more precisely, the non-ideal magnetohydrodynamic effects that come with it. So it turns out that those non-ideal MHD effects are the ones that determine whether the MRI is active or not. And with non-ideal, we just mean that the magnetic field is not perfectly coupled to the disk material. It can slip through the gas flows. And it turns out this is pretty important. But what we would have to do this precisely, we would have to conduct full non-ideal MHD simulations of the very inner regions of a disk over thousands of years to capture those instability cycles, and ideally in 3D as well. But with our current numerical methods, this is way too expensive and not feasible. So we have to find a way to get around those limitations. And this is what we did. We came up with a method, or we did not come up with it, but we applied a method that I have very creatively called pseudo non-ideal magnetoradiation-hydrodynamics, which just sounds super cool, but it is less spectacular than it sounds. But we will not get into much detail about what this actually entails, but we will look at the effects that it has on the inner disk structure. So for episode 3 of our project, which was submitted some time ago, we are looking at where is the MRI active and where it is. And up until now, we had only this simple temperature threshold, which led to an MRI active region that looked like this, these hatchet areas here in this region, with a simple transition around an activation temperature. But now, to improve upon this, we have tied the MRI activity to the presence of magnetic fields that we put into the inner disk. And they consist of a stellar and a disk component. And a little bit for the experts in the room, the non-ideal MHD effects that we consider are ambipolar diffusion and ohmic dissipation. And if we now run our models again with this new improved description, we get MRI activity regions that look like this. And so we can see on first glance that this is very different. So we go over from a simple linear transition or radial transition into this layered structure of the MRI active region that converges towards the midplane as we get closer to the star. I've also overplotted this black dashed line here, which is where the MRI would be active if we still used the old temperature threshold description. And we see that this structure here would already be in the outburst state. But in the new description, this is still stable. So the question arises, of course, can we still get in the outburst state? Can we still get this instability mechanism to go? And the answer is yes, we can, but with a significant twist. So here we see the same structure that we just saw with the MRI being active in between those black lines. And here we imposed a relatively weak stellar magnetic field of 1 kilogauss. And if we evolve this now in time, what we see is that we still get a burst, but it seems to get stuck here at about 0.2 AU. It cannot traverse further into the disk. And this is happening a lot more frequently now than what we saw before. So before we had quiescent phases of thousands of years, now we only have a few hundred. And we also don't see this reflaring anymore. We only have one spike in the accretion rate and going back to quiescence very, very quickly. And this, of course, also has very different effects on the inner disk structure. But this is what we will get in a few minutes. But it turns out that what we have just seen is just one burst mode of in total 4 different modes that we have identified in our models. So here we imposed a relatively weak stellar magnetic field that led us to a so-called narrow burst mode, where the region that the burst is affecting is very narrow in the disk and without any reflares. But if we increase the stellar dipole field, for example, we can get the reflares back again, but still remain in the narrow burst mode. But if there is a narrow burst mode, there's probably also a wide burst mode, and indeed there is. If we switch on a disk magnetic field as well, we get a reflaring wide burst mode, and this is exactly the same that we always had before in our simple models. So even with this super complicated new description of non-ideal radiation magnetohydrodynamics, we still recover the results that we got in the very beginning. But it turns out that this is only one possible scenario among 4 different modes that we have identified. And if we choose yet another magnetic field configuration, we get again a wide burst mode, but without reflares. So this tying of the MRI activity to the magnetic fields has led to 4 distinct burst modes. It doesn't even seem to be a spectrum on which those burst modes lie. They seem to be distinct from each other. And the only thing that separates those 4 models is the magnetic field description. Everything else is exactly the same. So this shows us yet again that if we take magnetic fields a little bit more seriously, it completely shifts our understanding of certain astrophysical processes, and the inner disk evolution is no exception to that. So there is also a big difference between the modes when it comes to the inner disk structure and its evolution. So here we see the wide burst mode, so that's the same that we had before with our simple models in a space-time plot. And here again, we see 2 such outbursts occurring, and each outburst is producing pressure bumps that are fading away after a few hundred local orbits. But there is this one pressure bump here that is very stable and strong over a relatively long period of time. And this is the one that has been known in the literature for some time. And so in this wide mode, we have one quasi-stationary pressure maximum that is only destroyed during the bursts. But this is still capable of trapping a lot of material within it and still be a good candidate for explaining the planets that we see in the inner disk. But if we go to the narrow burst mode, there is no such stationary pressure maximum present in the inner disk. We still have this pressure maximum here at the inner dead zone edge, but it's never in a stationary state. It's always oscillating because of this periodically occurring outburst. And this may pose a significant problem for the formation of the planets in the inner disk. But of course, to find out how significant this is, we have to follow up this further with dust simulations and with actual planet formation simulations put into this context. And this is something that is being worked on right now as well. Okay, so let's sum up of what we have found in this project here. So in episode 1, we saw that the inner disk structure is intrinsically unstable, and it's producing periodic accretion outbursts that completely rearrange the density structure of the inner disk and can have major consequences for the formation and migration of planets. In episode 2, we saw that while the opacities have a strong impact on the structure of the inner disk, they don't seem to influence the instability mechanism all that much. And in episode 3, we saw that the morphology of the burst and the outburst mechanism is highly sensitive to the magnetic field strengths that may be present in the inner disk. And they establish 4 distinct burst modes, with each burst mode having its very own accretion burst signature and its very own effects on the inner disk structure. And at the end, I would like to show something that has been basically in the works for 3 years. This is one simulation where I put everything that I did for my PhD and every description that I came up with into one simulation and ran it for some time to see how the burst reacts. But this time, we are not doing that only in 2D, as we always did in the previous models, but in 3D. And this just makes everything much cooler from the get-go. So up here, we see the same density, the temperature map that we always saw before. And this is a narrow burst setup, which means that we expect the burst to go until like 0.2 or 0.3 AU. Down here, we see the surface density. Here is where the accretion rate will appear, but this is not super interesting for now. Probably the most interesting panel is that one up here. So here we have the radius on the x-axis and the azimuth on the y-axis, going from 0 to pi. So we are looking at half a disk being stretched out into a rectangular shape. And the quantity that is plotted here is the so-called vortensity. So it's not super important to understand what it exactly is, but this is the quantity we look at when we want to determine if there are vortices in the disk structure. So if there is a vortex created in the inner disk, we will see that in this quantity. So to be more precise, we will see a strong minimum in this quantity when a vortex is present. So let's evolve this in time, and we see that the burst expands as expected and gets stuck here. But now, here we see something cool. Didn't that look cool? So there were multiple vortices produced as a consequence of this outburst. And after quite a short time, all those multiple vortices are merging into one massive vortex, which is this one here, that spans around about a quarter of the whole disk. And this is something that has at least been claimed to also have been observed in the inner disk with interferometry at a distance as small as 0.3 AU, which is exactly where we find this vortex as well. But until now, we have only looked at 2D maps of a 3D simulation, which is boring. So we look at a 3D rendering now. So here we see the temperature 3D structure of the burst. Here is the evolution of the vortices that are merging into one big, beautiful vortex that is going around the inner disk at a distance of about 0.3 AU. So this 3D simulation is just to show that no matter how far we think we are with those models, there's always more to explore, and it will definitely not get boring anytime soon. Especially if we increase the dimensionality of our models, we see a whole other layer of instabilities occurring. So this, for example, was the so-called Rossby wave instability. So we are not done probably anytime soon. And at the end, I would like to take a bit of a step back and put all those things a little bit more into context. So according to everything we know right now about the inner disk, it seems to be the case that it needs to be unstable in one way or another. And it just happens to be the case that this unstable region is where we find most of the planets today, including the terrestrial planets of our solar system, and indeed including our very own Earth. But of course, it is way too early to say if this process here has anything to do with the early solar system. But there are some hints of it, and this is definitely enough to keep us going and to let us dream about the origins of our Earth. Thank you very much.
Thanks, Michael, for the very nice talk and very efficient talk, and understood everything, and we still have plenty of time. Okay, so questions from Michael?
Want to?
Yeah.
Yeah, I just have a question about the timeline on your simulations, because you said with magnetic field you can reproduce the same effects. This essentially what you're showing here, this bouncing, I think, of burst you said, but the time frame are completely different, right? The magnetic field was thousands of years,
Yeah.
and now magnetic field you get the same effect, but it's compressed in tens of years. And with this, because I mean, this doesn't sound like a cosmic timescale. To me, at least, I don't know. I'm not an expert, but I'm just wondering, isn't this kind of timescale essentially for 100 years you have some instability, but after that it stables, right? Or does it go back to this state again?
So in this specific simulation, the green one here, we just didn't run long enough to see a second instability cycle. So if we would have evolved this green model here for like multiple thousands of years, we would see the exact same timescales that we always saw before. So the burst itself, it only takes tens of years. That was exactly the same before as well. The quiescent phase in between the bursts is the one that takes the longest, like thousands of years. But we just didn't evolve this model during the quiescent phase long enough to see a second burst.
Yeah, but why? What after hundreds of thousands of years?
Yeah. So eventually, of course, this accretion burst mechanism will stop because the inner disk or the disk itself will not be massive enough to trigger another burst. The big question is, when does it stop? And this is something we don't know yet, because what I want to try to do in the future is to couple those short time scales of our simulations here, so thousands of years, with something that can reproduce or can simulate much longer time scales, like millions of years. And only then we can determine when exactly is the point when this outburst mechanism stops. But this is still a matter of investigation.
Maybe a very basic question, but you had this very beautiful 3D simulation, and there's all of the stuff you worked on before going into that. How complex does this simulation get? What simulation setup do you use, and how long does such a simulation take?
Oh yeah, where do I start? So this kind of simulation is extremely expensive. So we are dealing with regions of the inner disk that are very close to the star. So everything is happening on very short time scales, which means we need to have a very high resolution, but the time steps we can take are very small. So we can run these simulations to simulate the time of hundreds of years, but this takes weeks to finish, on the order of weeks. And within those weeks, we have to use computational resources of, I think we used 8 computational nodes, each with 72 CPUs running for weeks. That's how we got the 3D run.
Thank you so much. A very exciting talk and also very well delivered, I would say. I had a comment for the gas opacities, because I mean we are still looking at the left side, very close to the star.
Yeah.
Okay, your radiative transfer gives you some kind of temperature that's probably in the order of thousands of Kelvin. And just to explain, so there, when you look at LTE opacities, you have a lot of water in it, and they make so low vibrational lines, so the gas becomes very opaque. However, so close to the star, what my models suggest, that this is basically an X-ray plasma. So it's completely ionized. Molecules are just not stable there. They are just destroyed. And then you end up with atoms and mostly ions, and they basically have zero opacity. Yeah. They don't really stop the infrared radiation from the star. So I think yeah, you say that maybe, you know, gas opacities should not be neglected, but then if you use LTE gas opacities, it's certainly an upper limit.
Yeah, I completely agree. Like we are aware of that, and we also wrote that in the publication. That we don't claim, we don't claim that we get the temperatures up here right. The only thing we claim is that even when, let's say, the main point of this publication was that even when we use very different descriptions for the opacity, this still does not interfere very much with this instability mechanism. That was the main point. Yeah. And also, when it comes to the positions of those transitions in our opacity description, the new one, we used just much higher gas opacities, and then we observed what we expected, that those transitions shift closer to the star, right? And if we now said, well, we have no gas opacities, or much lower gas opacities, then we expect the transitions to shift a little bit more outwards. So this is the conclusion that we made, but you're absolutely right. We cannot claim that we get the temperatures up here or the opacity is exactly right.
Then I have a question. I think a couple of slides back, you showed the density increase kind of close to your left side of your box. And I wonder, you know, this increase of the density, surface density profile, this one, for example. So you see there's a kind of logarithmic increase on relatively short things. This is exactly what we need in order to explain the JWST observations, as I showed you on Tuesday. So a kind of hard edge doesn't do it. We need something kind of softly increasing. But my question is that somehow related to your boundary condition on the left? So how do you, what does it mean that you get this kind of increase, slowly, soft increase?
So you mean the slope of the, so that's a topic that we have discussed about a lot. So it is not affected by the inner boundary. The inner boundary is at about 0.05 AU. This slope is determined by the transition in turbulence between the MRI active and the inactive region. So we use basically a simple alpha description, and we can artificially smooth out this transition between the MRI active and inactive region. So it does not jump immediately, but it is a smooth transition. And this transition in alpha leads to a smooth increase here in the density. In our newest models with the magnetic fields and the MRI activity tied to that, what we find is that theoretically the transition is actually very sharp, which is not what we want to have. But this is also something that other researchers have found when dealing with the non-ideal MHD terms. They found that the transition and the activation of the MRI is actually within a very narrow radial range. So I think this is still up for debate. What actually produces a very smooth transition? We are right now agnostic to that, to what actually produces it. And we are making it as close as possible to what the non-ideal MHD terms tell us, but still to be numerically stable.
One, two questions there.
Hi, nice talk. I have a question regarding the disk, because disks can be around other systems as well, like not just beyond stars, but there's a outbursts. Would you expect the same accretion variability in those kind of systems? Or?
So there are models and observations of such accretion outbursts around white dwarfs. That's I think the dwarf nova phenomenon.
Cataclysmic variables.
Cataclysmic variables, exactly, yeah. And the process is very similar to what we saw here. Actually, I started off comparing my models to the dwarf nova or cataclysmic variables models, and I saw that they are acting in almost the same way. So I would say yes, it is possible around other objects as well.
My question is, so you showed us this multiple pressure maxima.
Yeah.
Do they flatten out by the end of the quiescent phase, or how does it look?
Yes, they do. So we can see this here as well. So the pressure maxima are here produced, and they're associated with those bumps that we see here. But after some time during the quiescence phase, you see up here, there are no bumps left. So they are smoothed out during the quiescent phase because of the viscous evolution that is still taking place in the dead zone. If there were no viscous evolution in the dead zone, and you would put such a pressure bump in there, it would just stay there. But here in our models, the dead zone evolves viscously as well, and that smooths out the pressure bumps over time.
Well, thank you for this very nice one. But, I would be curious, so a simple question is, do your models include chemistry?
Oh.
But, okay, then the next question makes more sense now, because you are talking sensibly a lot about non-ideal MHD, and in order to determine its effect, one would want to know the degree of ionization, local degree of ionization.
Yeah.
Do you maybe want to say a few words how you circumvent the knowledge about this?
Of course, yes. So we are relying on work from the literature, of course, and there has been work done, for example, in 2015 by Stephen Dash and Neil Turner, who calculated the non-ideal MHD coefficients, the diffusivity coefficients, based on a thermochemical model. So we have basically left them to do the work on the chemistry, and we used their results in our simulation. So we took the diffusivity coefficients from their work, from that thermochemical model, and they are dependent on things like temperature, on the density, on the external ionization, and on the plasma betas, on the magnetization. And those are the parameters that we can calculate from our models. And then we interpolated tables of diffusivity coefficients. And we used those coefficients to determine of whether the MRI is active or not.
Any other questions?
I'm curious about topology of the magnetic field which you prescribe. You mentioned the dipole field of the star and a mystic for me accretion disk or disk magnetic field. What does it mean? What kind of the field? So that I'm trying to imagine the general topology of the magnetic field, and
disk field, you mean?
In total, because the rotating dipole in the conducting medium like plasma would not be dipole anymore. So there will be other non-dipole harmonics, colloidal harmonics, it will spiral. How is your magnetic field?
Yeah, that's a very good question. So the work on magnetic field topology within disks has been relatively sparse in the literature, and that's still a matter of current research. What we did here was we took basically the simplest approach possible. For the disk magnetic field, we just prescribed a purely vertical magnetic field. So it does not have a radial component within it.
What is then the difference with the dipole field? It will be also vertical.
Yeah, the dipole field is also threading the disk vertically. But with dipole, I mean that the strength of the magnetic field is falling off as described by a dipole. So with 1/r to the third. So it starts very strong from the stellar surface, and it's dropping off very quickly into the disk.
So this means that your magnetic field is always normal with respect to the plane of the disk. And
yes.
The value changes with the radius.
Exactly, yeah. Because this is what matters when we want to determine the magnetic field strength is what matters when we want to determine the MRI activity. We do not evolve the magnetic field in any way.
The mutual components would change a lot.
Yeah, I know. Yeah, right. Yeah.
Magnetic field is very likely.
Yes, yes. But we are relying on the strength, and we use the simple description by just assuming it's vertical. But I mean, of course, a very promising venue forward would be to evolve the magnetic field as well, see how the azimuthal component contributes and then recalculating this.
You can adopt, since magnetic field is anyway a parameter of your model, it is not self-consistently calculated. It's already enough complex.
I agree.
But you may adopt an approach that you consider the parameterized magnetic field as a set of spherical harmonics. Dipolar, toroidal, and so on, quadrupolar. This would probably allow you to somehow emulate the possible magnetic field complexity, and then you can conclude about the effects of the magnetic field more decisively present.
Yeah.
But might be.
I mean, actually, Kunnan's models have a little bit of evolving the magnetic field in it. Maybe you want to explain yourself, but so there's something in the very beginning from the cloud, and once the matter actually is transported inwards, they drag this field. So initially it's straight, but then as the matter is accreting towards the star, it gets this kind of slanted shape, and that this angle is actually very important. It's discussed being substantial for the disk evolution in terms of winds, because then you can lose some angular momentum when you send winds along these magnetic fields. So this would be the next, maybe the most simple thing you can do is to have it kind of frozen into your matter. This is what Kunnan is doing. Yeah, anyway.
Okay, any other questions? Okay, I have a quick question, and then maybe we can go home. Easter. What's pseudo about your methods, and do you expect Hall effects to change anything, or it's significant in your estimations?
So what's pseudo about it is that we cannot afford to evolve the full non-ideal MHD equations in addition to the radiation transfer that we are following. So the pseudo is we are just approximating the non-ideal MHD effects with the diffusion coefficients that I've mentioned before. So we are implementing them, we are not calculating them ourselves. That's what I mean by pseudo. And what was the second question?
The Hall effect.
The Hall effect, yeah. Yeah, we don't know. That's the easy answer. I mean, the Hall effect, when we include the Hall effect, then it also depends on the polarity of the magnetic field, and this has different effects that can lead to the Hall shear instability that can mess up the whole structure. Like this is something that another 3 PhD students have to work on probably.
Okay, I agree. Okay, let's thanks Michael again.